Hey CW Apes, Mr. Kennedy here with part 2 of your chapter 19 lecture video on water pollution. At this point, we're going to kind of shift gears and look at some water pollution that maybe falls along the lines of, natural pollution as opposed to man-made. So we're going to start and dive in to this kind of pollution by looking at toxic tides. There is a natural process that occurs in our oceans that would cause certain types of organisms called dinoflagellates to reproduce in large numbers. Dinoflagellates create what we call red tides. Dinoflagellate blooms have become increasingly common in slow-moving and shallow waters. These dinoflagellates are algae-like creatures, and anytime you put excessive amounts of nitrogen or phosphorus into the water, they're going to reproduce like crazy. It's just like putting fertilizer on your lawn. When these dinoflagellate numbers rise, at the end of the day, the water becomes murky, becomes difficult to see through, and anything that eats these dinoflagellates will then pick up the toxins that their body contains and ultimately be inedible within the food chain. Okay, so we can actually have toxic tides that occur naturally. One interesting thing about dinoflagellates and red tides is that if you go to the ocean during a red tide at night and watch the waves crash, red tides will actually create kind of a blue-green bioluminescence in the surf. And if you drive a boat through it, the prop wash will do the same thing, because many dinoflagellates can also bioluminesce, which is pretty cool. Okay. Something else to think about when we think about water pollution is thermal pollution. I know that sounds odd, but when you think about the ocean and the creatures that live there, they become acclimated to specific temperature ranges. So effluent from industrial plants or even nuclear reactors can actually change the temperature of the seawater that these creatures are exposed to. The problem that creates is, if it's outside of their range of tolerance, it can be deadly to them. Not only that, but warmer water holds less dissolved oxygen. So with less dissolved oxygen, you get less sea life, right? The lack of oxygen can literally cause the entire food web to collapse in a positive feedback loop that, once started, might be impossible to stop. Think of it this way. The water temperature goes up, so there's less dissolved oxygen. That kills sea life. As the sea life dies and decomposes, that decomposition process pulls more oxygen out of the water. So that ultimately causes more and more death. See the problem? Okay, so that's why thermal pollution is a big deal. Raising or lowering water temperature from normal levels can adversely affect water quality and aquatic life. Oxygen solubility in water decreases as temperature increases. Species requiring high oxygen levels ultimately are adversely affected by that warm water. So anytime humans discharge hot water into the ocean, we're contributing to this problem. Industrial cooling processes, nuclear reactors, they're the culprits. They often are right there by the coast, and they basically pull in the cold water, use some sort of heat exchange system, and then they'll pump out the hot water in what we call a thermal plume. And it disrupts natural ecosystems. It causes die-off of heat-sensitive organisms. You might even get invasive species, because there will be some organisms that are attracted to the warmth, but maybe die off later when, the factory or the power plant backs off on its production or stops the effluent. So at the end of the day, no matter how you look at it, thermal pollution is bad. Oxygen demanding waste. So when we think about oxygen demanding waste, we're going to make a full circle back to that human and animal waste thing that we talked about at the beginning of all of this in our first video, when we were looking at organic and inorganic waste products that sometimes end up in our waterways. Now, how is waste sewage an oxygen demanding thing? Well, the sewage decomposes, and it's that decomposition process that depletes the oxygen in the water, or basically pulls the oxygen out of the water. We can measure how much oxygen is in the water by doing what's called a BOD test, or biological oxygen demand test. The BOD measures the amount of dissolved oxygen needed by aerobic decomposers to break down the organic matter in a certain volume of water in about a 5-day incubation period. Okay, so we'll use that to determine how much biological oxygen demand is being put on the water. Water with an oxygen content of about 6 parts per million will support desirable aquatic life. If that parts per million oxygen drops to below 2, well, then you'll get detritivores and decomposers. Oxygen is added to the water by diffusion from wind and waves and by photosynthesis. Oxygen is removed by respiration and then this oxygen consuming process of decomposition. Okay? Now, when you think about oxygen demanding waste, right, remember, the biochemical oxygen demand is the amount of dissolved oxygen consumed by aquatic organisms, and you use that as a test of organic waste contamination from sewage, paper pulp, and food waste. Okay, and then the dissolved oxygen content is a measure of the dissolved oxygen in the water, and the effects of oxygen demanding waste on rivers depend on volume, flow, and temperature. Okay, so we're going to skip through a couple of pictures here just to kind of keep things moving along and go to plant nutrients and eutrophication. So plant nutrients and eutrophication can affect your water quality basically by taking what was once clean, clear water, turning it dark, and making it unpotable. Eutrophication is the process of literally taking something that was once like crystal clear and having it turn like dark green, okay, or black almost. And this happens as a result of what we've just kind of talked about here with the process of organic material being dumped into a waterway, algal individuals like blooming or growing in mass, dying and decomposing, and like this whole cycle just like happening over and over and over again. Eventually, at the end of a eutrophication cycle, you could even have your body of water completely fill in. Okay, so there's some vocabulary here that you need to get under your belt, right? Like oligotrophic. Oligotrophic, these are bodies of water that have clear water and low biological productivity. Eutrophic, these are bodies of water that are rich in organisms and organic material. Eutrophication is the process of increasing nutrient levels and biological productivity, which is, again, kind of like a normal part of succession, but accelerated by people. That's what the cultural eutrophication is all about. Increasing biological productivity caused by human activities that create algal blooms. Okay, so here's a picture of natural eutrophication, where the natural like ebb and flow life cycle of the surrounding plants and animals eventually adds organic material to a body of water, and it slowly fills in over time. This could take centuries for this to happen. In cultural eutrophication, humans greatly accelerate the process by adding fertilizer runoff from farms, industrial processes, or even phosphate-laden detergents that create the algal bloom, and everything like is highly accelerated from there. This is another picture of the steps of eutrophication. So we have nitrogen or phosphorus added to the water. This causes an algal bloom. The algae begin to die and sink, and then the dead algae is food for bacterial decomposers, and our biological or biochemical oxygen demand increases. And as that increases, then the oxygen decreases, anaerobic bacteria increase and produce hydrogen sulfide and methane. And now what was once awesome, like clean water, kind of smells like rotten eggs and nobody wants to be in it. And over time, right, that body of water kind of turns into marsh or swamp, and then eventually dries out and becomes, land. Okay. Now, how do we control eutrophication? Well, real simple. Okay, we reduce the amount of nitrogen and phosphorus flowing into our waterways. You can do this by, first of all, not like depositing nitrogen and phosphorus containing materials into the water, or you can use biofiltration. Biofiltration, in this case, sewage can flow through wetlands designed to remove nitrogen and phosphorus. Detergents and fertilizers can be used sparingly, or we can opt to use phosphate-free varieties. So there's lots of things that we can do. Control industrial runoff, control urban runoff, control acids from mines, protect our wetlands, ban and regulate phosphate detergents. These are all things that are easily managed and steps that we can all take to protect our water. Let's finish today by looking at what our water quality is like today, and then maybe a couple of laws that have been passed to help protect our water. So areas of progress. The Clean Water Act in 1972 established a national pollution discharge system which requires a permit for any entity dumping waste in surface waters and requires disclosure of what's being dumped. At the end of the day, this improved water quality dramatically, mostly due to sewage treatment. The goals have not been fully met, though. 21,000 water bodies do not meet the guidelines for designated uses. In 1998, the EPA switched regulatory approaches, and rather than issue standards on a site-by-site basis, the focus is now on watershed-level monitoring and protection. States are required to identify waters not meeting water quality goals and to develop, a maximum daily load for each pollutant in each listed body of water. Some of the greatest impediments to achieving the national goals in water quality are sediment, nutrients, and pathogens, especially from non-point sources. They're hard for us to track down. Since they're hard for us to track down, it's even harder to stop. About 3/4 of water pollution in the U.S. come from soil erosion, air pollution, fallout, like air pollution fallout, right? And agricultural and urban runoff. A cattle feedlot can produce 144 million tons of manure. Where's all that go? And every time it rains, you bet all that nitrogen and phosphorus can run off the feedlot and end up in waterways. Even pet waste, right? Pet waste does not go through sewage treatment. So if it's piling up in flower beds and on lawns and then you turn on the sprinklers, the rest should be self-explanatory. Other countries also have water pollution. It's not just a U.S. thing. Sewage treatment in wealthy countries of Europe generally equals or surpasses the U.S. In Russia, only about half of the tap water supply is safe to drink. In China, 70% of surface waters are unfit for consumption. The poorest countries in South America, Africa, Asia have disastrous water quality due to poverty, pollution growth, and shift from polluting industries from countries where laws are strict to where they are lax. The Yamuna River and 2/3 of the other surface waters in India are so polluted that it's dangerous to even have contact with the water. Okay? So what do we do about it? If we can't drink the water, maybe we should go for bottled water. Is bottled water safe? Well, Americans buy 28 billion bottles of water annually, which adds up to around $15 billion. Worldwide, 42 billion gallons of water are bottled. 80% of bottled water purchased in the U.S., literally just the bottles end up in landfills. And when you think about what water is being put in this bottled water, at the end of the day, most of it is from a municipal source, which basically equals tap water, and people don't realize what they're drinking, okay? Municipal water is often safer than bottled because most large cities test their water supply every hour for up to 25 different chemicals. Groundwater is hard to monitor and hard to clean. About half the U.S. population and 95% of rural residents depend on groundwater aquifers for drinking water. For decades, groundwater was assumed impervious to pollution. Unfortunately, that's no longer true. The EPA estimates 4.5 trillion liters, of contaminated water seep into groundwater in the U.S. every single day from septic tanks, cesspools, landfills, waste disposal sites, and the like. 1 gallon of gasoline can make 1 million gallons of water undrinkable. In ag areas, fertilizers and pesticides contaminate aquifers and wells, and those contaminants can last literally for thousands of years and travel through the aquifer the same way they could travel through a body of water above ground. Okay? In addition to groundwater contamination, surface waters can make drinking water unsafe. In 2008, the EPA data shows that 30 million people in the U.S. get their water from community systems that don't meet all health-based drinking water standards. An estimated 1.5 million Americans fall ill from fecal contamination annually just by drinking water. There are a few controls on ocean pollution. Coastal zones, bays, estuaries, and reefs are often overwhelmed by contamination from heavy metals, toxic chemicals, oil, pathogens, and sediment. Discarded plastics, non-biodegradable things, again, can last for years out in the ocean and be carried around the world on currents. They often ensnare birds and mammals and can choke them. Okay, so very few controls on ocean pollution. And even if somebody like California decides, you know what, we're going to ban plastic bags, if California is the only state along the western front of the United States that does so, then, does it matter? Because the water is going to keep right on traveling past California and Oregon and Washington and Canada and Alaska and swirl its way around to Japan. And if everybody else is still dumping plastic in, right, then we're still going to have a problem. What we're talking about is a global problem, not a California problem, not a United States problem. It's a global issue that needs to be addressed. So at the end of the day, we need to really reduce what we're putting out in our water, okay? We know that water is the universal solvent. We know that it can pick up anything and just about everything we put in it. The cheapest and most effective way to reduce pollution is to avoid producing it in the first place or avoid releasing it into the environment. It's simple, simple, simple. Studies show that as much as 90% less road salt can be used without significantly affecting safety. We can carefully dispose of oil. We can recover metals from industrial waste and sell them. We can eliminate the use of lead in gasoline. We can, even like work with agriculture, urban runoff, construction sites, and land disposal to reduce the amount of pollution that ends up in our waterway. Soil conservation methods can also help protect our water quality. Reducing materials carried away by stormwater, by having, surface water treatment plants that can catch this stuff is a great step in eliminating or at least reducing the amount of load that goes into our rivers, lakes, and streams. Okay. More than 500 pathogenic bacteria, viruses, and parasites can travel, from human or animal excrement through the water. So just eliminating that alone is a huge first step. In many poor countries, outdoor urination and defecation is pretty much the norm. If we could provide wastewater treatment on a global scale, think of the impact that we could have, okay? So when you think about what we can do to reduce water pollution, think about these things. All right, ladies and gents, I think I have one more slide here to share with you. I'm going to skip over this water treatment thing because I've actually already done a video for you. And here's that last slide on water legislation. So again, coming back to the Clean Water Act, this is our best piece of legislation to protect our waterways. Its goal was to return the U.S. Surface waters to a fishable and swimmable condition by tracking point sources and non-point sources to the best of our ability and set goals for management, right? Set goals to reduce the amount of pollution in our local waterways and to hold people accountable for the pollution that they were creating, okay? So ladies and gents, that's the good, the bad, and everything there is in between about water pollution. I hope you've learned a lot. and have enjoyed this. I'm Mr. Kennedy, and I will see you next time.